Welcome to this detailed explanation of Stone Game 5, a problem that can be solved elegantly using interval dynamic programming. At first glance, this problem looks like a game where we simply need to decide where Alice should split the stones. However, the difficulty comes from the fact that every decision changes the remaining rows of stones, and that remaining row determines all future decisions. So, in this presentation, we will start by understanding the game carefully, then identify the dynamic programming state, derive the recurrence, optimize range sum calculations using prefix sums, walk through examples, and finally analyze the complete C++ solution and its complexity. The most important concept to take away from this problem is how to recognize when a game or recursive partitioning problem can be modeled using interval DP. Let's first understand exactly what happens during the game. We have a row of stones and every stone has an associated integer value. During each round, Alice must divide the current row into two non-empty parts. Bob then calculates the sum of the values in both parts. The important rule is that Bob removes the part with the larger sum. Alice receives the sum of the part that remains. There is one special situation. If the two sums are equal, Bob allows Alice to choose which side gets removed. Therefore, Alice can decide which side should survive. After that, the same process continues on the remaining stones. The game ends when only one stone remains. Our objective is to determine the maximum total score Alice can achieve by making the right sequence of splits. The input is an integer array called stone value. Each element represents the value of one stone. The constraint allow up to 500 stones and every stone can have a value as large as 1 million. The output is a single integer representing the maximum score Alice can obtain. There are two important observations here. First, Alice does not directly decide which side survives except when the sums are equal. Second, Alice's decision is not isolated to the current round. A split determines the remaining interval, and the remaining interval determines all future possibilities. That second observation is what eventually leads us to dynamic programming. Let's understand one complete round using the first example. Suppose our stones are 6, 2, 3, 4, 5, and 5. Alice decides to split them into two halves. The left part contains 6, 2, and 3, while the right part contains 4, 5, and 5. The sum of the left side is 11. The sum of the right side is 14. Because 11 is smaller than 14, Bob removes the right side. Alice receives the value of the surviving side, which is 11. The next round therefore starts with the stones 6, 2, and 3. Notice something very important here. The discarded stones are completely irrelevant after this point. The entire future game depends only on the surviving contiguous portion. This is the structural property that makes interval dynamic programming possible. A natural first thought might be to use a greedy strategy. For example, perhaps we could always choose the split that gives Alice the largest immediate score. Unfortunately, that does not work reliably. Why? Because the score Alice receives in the current round is only part of the final answer. After receiving that score, Alice gets another opportunity to split the surviving interval. So we actually need to think about two things simultaneously. The score Alice gets right now and the maximum score she can obtain later from the surviving interval. A split that gives a slightly smaller immediate score could leave behind a much better interval and therefore produce a larger total score. This is exactly the type of situation where dynamic programming becomes useful. Let's make that idea more concrete. Imagine one split gives Alice an immediate score of 10, but the remaining interval can provide only 5 additional points. The final score would be 15. Now imagine another split gives Alice only 8 points immediately, but the remaining interval can provide 12 more points. The final score becomes 20. So choosing the largest immediate score would have been wrong. The correct objective is current score plus the best possible future score. This is a classic optimal substructure pattern. Once you know which interval survives, the future game on that interval is exactly the same type of problem. That means we can solve smaller interval once and reuse their results. Here is the most important observation in the entire problem. After every round, exactly one contiguous part of the current row survives. For example, suppose we have 6 stones. Alice splits them into the first 3 stones and the last 3 stones. Bob removes one side. Only one contiguous interval remains. Now the next game is played entirely inside that interval. So instead of thinking about the complete history of the game, we can simply ask, what is the best score Alice can obtain from this particular interval? That gives us a natural dynamic programming state. This is why the problem belongs to the family of interval dynamic programming problems. Interval dynamic programming is used when the state of a problem can be represented by a contiguous range. The typical state is written as dp(L)R, where L is the left endpoint and R is the right endpoint. In this problem, dp(L)R means the maximum score Alice can obtain when the current row consists of the stones from index L through index R. Once we define this state, the problem becomes much more manageable. For every interval, Alice can try every possible split. Each split produces a smaller interval, and those smaller intervals already have answers stored in our DP table. Let's formally define our state. DPLR represents the maximum score Alice can obtain from the subarray starting at index L and ending at index R. For example, if we have DP14, this represents the optimal score Alice can achieve when the current stones are stone value 1 through stone value 4. Now consider the smallest possible interval. If L equals R, there is only one stone. Alice cannot divide one stone into two non-empty rows. Therefore, no more score can be earned. So our base case is DPII assigned 0. This is also why our DP table can initially be filled with zeros. Now suppose we are solving an interval from L to R. Alice can choose any valid position k between L and R minus 1. The split becomes L dot 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 k plus 1 dot 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 R. For example, if the interval contains 5 stones, Alice has 4 possible split positions. Every one of these splits can lead to a different survival interval and therefore a different future score. So we cannot simply examine one split. We must examine every possible split and determine which one gives Alice the highest final score. This is the central transition of our interval DP. For a particular split at position k, we need two quantities. The first is the sum of the left interval from L through k. The second is the sum of the right interval from k plus 1 through R. Let's call them left sum and right sum. Bob compares these two values. If the left sum is smaller, the left side survives. If the right sum is smaller, the right side survives. And if both are equal, Alice gets to decide which side survives. So the entire DP transition is determined by this comparison. Let's consider the first case. Suppose left sum is less than right sum. Bob always throws away the row with the maximum value. Therefore, the right side is discarded and the left side survives. Alice receives the value of the surviving side, which is left sum, but the game does not end there. Alice can continue playing on the left interval. The best score she can obtain from that interval is already stored in DPLK. Therefore, the total score for this split is left sum plus DPLK. We compare this candidate with the best result we have already found for the interval. Now consider the opposite situation. Suppose left sum is greater than right sum. The left side has the larger sum, so Bob removes the left side. The right side survives. Alice receives right sum points. The future game is now played on k plus 1 dot 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 r. The best score obtainable from this remaining interval is dp k plus 1 r. Therefore, our candidate answer for this split becomes right sum plus dp k plus 1 r. Again, we compare this candidate with the other possible splits. Now we have the most interesting case. Suppose left sum equals to right sum. Bob does not automatically remove one side. Instead, Alice gets to choose which side should be discarded. This means Alice can choose whichever surviving interval gives her the best future score. The immediate score is the same regardless of which side survives because both sides have the same sum. Therefore, the candidate becomes left sum plus max of dplk, dpk plus 1 r. We add the common sum once and then choose the better of the two possible future states. This equal sum case is extremely important. Forgetting it would make the entire solution incorrect. We can now combine all three cases into one recurrence. For every interval L r, we try every possible split k. Let capital L represent the left sum and capital R represent the right sum. If capital L is smaller than capital R, the candidate is capital R plus dp Lk. If capital R is smaller than capital L, the candidate is capital R plus dp k plus 1 R. And if they are equal, the candidate is capital L plus max of dp Lk, dp k plus 1 R. After calculating the candidate, we update dplr with the maximum candidate found over all possible split positions. This gives us the complete dynamic programming recurrence. There is one remaining problem. Our DP tries many intervals and many split positions. For every split, we need to calculate two range sums. If we calculate each range sum by looping through all its elements, the algorithm becomes unnecessarily expensive. Instead, we use a technique called prefix sum. Prefix sums allow us to calculate the sum of any contiguous range in constant time. This is especially useful because our DP already has three nested levels of iteration. We don't want another loop inside the innermost transition. Let's use the array 6, 2, 3, 4, 5, and 5. We construct a prefix array beginning with 0. The prefix values become 0, 6, 8, 11, 15, 20, and 25. The interpolation is that prefix I contains the sum of the first I elements. For example, the sum from index L to index R can be calculated as prefix R plus 1 minus prefix L. So for the left part, the sum becomes prefix k plus 1 minus prefix L. And for the right part, prefix R plus 1 minus prefix k plus 1. Both calculations take constant time. Now let's discuss an important implementation detail. Our state dplr depends on smaller intervals. For example, when calculating an interval from L to R, we might need dplk or dpk plus 1 R. Both of those intervals are strictly smaller than L r. Therefore, we need to calculate smaller intervals first. We do this by increasing the interval length. First, we process intervals of length 2, then length 3, and then length 4, and we continue until the entire array is covered. This guarantees that every DP state we need has already been calculated. We create an n by n DP table. Every value is initially 0. This works because the base case is that a single stone contributes 0 additional score. So DP II assigned 0 for every position. We then start processing intervals of length 2. Why length 2? Because an interval of length 1 cannot be split. An interval of 2 is the smallest interval where Alice actually has a valid move. The first loop controls the interval length. We start at length 2 and continue up to n. The second loop determines the starting position L. Once L and the length are known, we calculate R assigned L plus len minus 1. This gives us a complete interval. Finally, the third loop tries every possible split position k. So conceptually our loops are choose interval length, then choose interval, then choose split. For every split, we calculate the corresponding candidate score. Inside the innermost loop, we calculate the two sums using our prefix array. The left sum is prefix k plus 1 minus prefix l. The right sum is prefix r plus 1 minus prefix k plus 1. Notice that there is no loop involved here. Each sum takes constant time. This is what allows our overall algorithm to remain within O of n cube instead of becoming even more expensive. Once the two sums are known, we simply apply our three-case recurrence. Now we translate our mathematical recurrence directly into C++. First, if the left sum is smaller, we update the dp state using left sum plus dp lk. Second, if the right sum is smaller, we use right sum plus dp k plus 1 r. Finally, if both sums are equal, Alice can choose the better surviving side. So we use left sum plus max of dp lk, dp k plus 1 r. Every candidate is compared against the current value of dp lr. The maximum candidate becomes the final answer for that interval. Let's now look at the complete implementation. We first determine the size of the array. Then we construct the prefix sum array. After that, we create the two-dimensional DP table. The outer loop processes intervals from smaller to larger. For each interval, we try every possible split. For every split, prefix sums give us the left and right values in constant time. Then we apply the appropriate transition based on the comparison between the two sums. Finally, after all intervals have been processed, the answer for the entire array is stored in dp0 n-1. So the implementation is a direct translation of the mathematical recurrence we derived earlier. Let's perform a dry run using 6, 2, 3, 4, 5 and 5. One optimal split is 6, 2, 3 on the left and 4, 5, 5 on the right. The left sum is 11, the right sum is 14. Because 11 is smaller, Bob removes the right side. Alice earns 11 points. The remaining interval is 6, 2, 3. So our game has effectively transformed from a 6-stone problem into a 3-stone problem. The important thing is that our DP already knows how to solve the smaller intervals. Now consider the remaining stones 6, 2, 3. Alice splits them into 6 on the left and 2, 3 on the right. The left sum is 6 and the right sum is 5. Because 5 is smaller, Bob removes the left side. Alice earns another 5 points. Her total is now 11 plus 5, which equals 16. The surviving stones are 2, 3. Again, the problem has become a small interval. This illustrates exactly why interval DP works so naturally here. We now have only two stones, 2 and 3. There is only one possible split. The left sum is 2, the right sum is 3. Bob removes the larger side, which is the side containing 3. Alice removes 2 more points. Her final score becomes 11 plus 5 plus 2, that equals 18. Therefore, the maximum score for the first example is 18. Our DP systematically examines all possible splits and finds this optimal sequence. Now let's look at the second example 7, 7, 7, 7, 7, 7, 7. All stones have the same values. This creates many situations where the two sides can have equal sums. Whenever the sums are equal, Alice is allowed to choose which side survives. This flexibility is extremely valuable. The optimal strategy allows Alice to accumulate 7 plus 7 plus 7 plus 7. Therefore, the final answer is 28. This simple example is particularly useful because it demonstrates why the equal sum case must be handled separately. The third example contains only one stone, 4. There is no possible split because Alice needs two non-empty rows. Therefore, the game ends immediately. Alice never earns any point. The answer is 0. This directly corresponds to our DP base case, DP II assigned 0. Whenever the interval contains exactly one stone, there is no action to perform. Let's establish why our solution is correct. For every interval, Alice can choose any valid split. Our algorithm examines every possible split. For each split, we correctly determine what Bob will do by comparing the two sums. If the left side is smaller, we continue with the left interval. If the right side is smaller, we continue with the right interval. If the sums are equal, Alice chooses whichever surviving interval gives her the better future result. Because the smaller intervals have already been solved, their optimal results are available in the DP table. Therefore, every possible decision sequence is represented through the recurrence. Taking the maximum over all possible first decisions gives the optimal answer for the current interval. By the same reasoning, DP 0 n minus 1 gives the optimal answer for the entire game. Let's analyze the complexity. There are O of n square possible intervals because we have two endpoints L and R. For every interval, we try up to O of n possible split positions. Therefore, the total time complexity is O of n cube. Now consider the space. We maintain an n by n DP table giving O of n square space. The prefix array requires an additional O of n space, but the dominant space usage is the DP table. So the final complexity is time big O of n cube and space big O of n square. The maximum number of stones is only 500. So although cubic complexity sounds large, the actual problem constraints are designed for this solution. The innermost operation is also very lightweight. We perform a couple of prefix sum lookups, some arithmetic comparisons, and maximum operation. There is no additional traversal of the interval. That is why using prefix sums is important. Without prefix sums, calculating the sums repeatedly could introduce additional work and make the implementation unnecessarily slow. With prefix sums, the intended O of n cube interval DP solution is practical for n equal to 500. Let's discuss some common mistakes. The first mistake is trying to solve the problem greedily. A split with the best immediate score might not produce the best final score. The second mistake is forgetting the equal sum case. When both sides have the same sum, Alice can choose the side that survives. The third mistake is repeatedly calculating range sums using loops. That makes the algorithm much slower than necessary. Prefix sums solve this problem efficiently. The fourth mistake is processing intervals in the wrong order. Since larger intervals depend on smaller intervals, we must process the DP states from shorter intervals to longer intervals. Keeping these 4 points in mind prevents most implementation errors. Let's summarize the reusable pattern behind this problem. We start with an interval. Alice chooses a split. The two resulting parts are evaluated. Bob determines which part survives. The surviving part becomes a smaller interval. Alice receives the value of the surviving part. Then the process repeats, so the general structure is choose a split, determine the surviving side, add its value, solve the remaining interval, take the maximum. Whenever you see a problem where an array or sequence is repeatedly divided into contiguous pieces and the future problem is restricted to one of those pieces, interval DP should immediately come to mind. Let's finish by summarizing the major ideas. The most important observation is that after every round, only one contiguous portion survives. That means the future game can be represented by an interval. We therefore determine DPLR as the maximum score Alice can obtain from that interval. For every possible split, we calculate the two sums. If the left sum is smaller, the left interval survives. If the right sum is smaller, the right interval survives. If the sums are equal, Alice chooses which side produces the better future score. Prefix sums allow us to calculate range solutions in constant time. The resulting algorithm has O of n cube time complexity and O of n square space complexity. The broader lesson is even more valuable than this particular problem. When a recursive problem repeatedly works on smaller contiguous ranges, look for an interval dp formulation. Once the correct state is identified, the complicated game can be often transformed into a systematic and efficient dynamic programming solution. Thank you for your attention.